Hello, today I'm going to work through a set of questions that you might typically get in an A2 level physics exam on electromagnetism. First, let's just review the formulae that you're likely to need. When a current flows in a wire and the wire is perpendicular to a magnetic field, there will be a force on that wire which will be perpendicular to both the magnetic field and the current, and that force will equal BIL, where B is the magnetic field, I is the current, and L is the length of the wire that is in the field. If the current is at an angle theta to the field, then the force is equal to BIL sine theta. When a current flows through a wire, it generates a magnetic field, and that magnetic field will equal mu0 I divided by 2 pi r, where mu0 is the permeability of free space, not to be confused with epsilon 0, which is the permittivity of free space. I is the current, and r is the radial distance from the wire. In a long solenoid, the magnetic field inside the solenoid will equal mu0 Ni, where n is the number of turns in the solenoid per unit length, and I is the current. When a beam of electrons, or indeed any charged particles, travels through a magnetic field with velocity v, and they're travelling, we'll assume, perpendicular to that field, then there will be a force on those charged particles which will be both perpendicular to the magnetic field and the direction of the charged particles, and that force equals B, the magnetic field, times Q, the charge on the particles, times V, the velocity. And you'll notice that if the velocity is 0, then the magnetic field has no effect on the charged particle. Compare that with an electric field, where even if the particle is not moving at all, the electric field will still exert a force on the charged particle. Then we define magnetic flux as the amount of a magnetic field going through a particular area, so phi equals BA. Where you have a solenoid, the flux linkage is BAN, where N is now the number of turns in the solenoid. Where you have a changing flux, you generate an EMF, electromotive force or voltage, and that will equal minus d phi by dt, which is the change of, or the rate of change of flux. If there is no change at all, there will be no EMF, and the minus sign is there to reflect Lenz's law, which says that the voltage will always be such as to oppose the change that caused it. Where you have a transformer, you can say that the voltage in the primary divided by the voltage in the secondary is equal to the number of turns in the primary divided by the number of turns in the secondary, and that equals the current in the secondary divided by the current in the primary. Notice in that case the two are inverted, and that of course is to keep power constant. In other words, VPIP is equal to VSIS. Power in the primary equals the power in the secondary. And then when you've got a generator, phi, the flux, will equal to BAN, that's the magnetic field, times the area times the number of turns, times sine omega t, where omega is the frequency, or at least omega is 2 pi times the frequency. And the voltage so generated will be, as we've said before, minus d phi by dt. And if you take the equation above and differentiate it with respect to time, you get minus BAN omega cosine omega t. Question 1. A wire carrying a current of 2 amps passes a magnetic field perpendicular to it of 3 times 10 to the minus 5 Tesla. What is the force on the wire? And here we're going to need the formula that F equals BIL, where the force is equal to the magnetic field times the current times the length of wire that's in the field, and I can tell you that the length of the field is 5 centimetres. So that means the force is going to be the magnetic field, which is 3 times 10 to the minus 5, times the current, which is 2, times the length, which is 5 centimetres, so that's 0.5 metres. And if you work that out, it should come to 3 times 10 to the minus 6 newtons. And if we're asked in which direction, then we need to apply Fleming's left-hand rule. We're going to assume that this is north and this is south, so the field is going downwards. So using Fleming's left-hand rule, the current is going to the right, so we use the second finger for the current to the right, but the field I've pointed in the wrong direction. I'm at present using field going upwards, and that results in my thumb coming out of the page. Now the field of course will go downwards, but I can't contort myself, but I have got a bit of an ability to do a bit of logic. If I've pointed the field in the wrong direction and my thumb is pointing upwards, if I pointed it in the right direction, my thumb would be pointing downwards. So the force on the wire will be into the page. Indeed, I have now contorted myself for the sake of science, and you can see the current is the second finger, the field is the first finger, and my thumb is pointing downwards. Part 2 of the question is, suppose that the wire, here is the field, that's B, suppose now that the wire is at 30 degrees to the field instead of being perpendicular. What now is the force on the wire? Well, here we will need the formula that F equals BIL times the sine of the angle between them, and sine 30 of course is going to be a half, so now we're going to get half of the value we got before, which is 1.5 times 10 to the minus 6 newtons. Question 2. A beam of electrons is travelling to the right at 4 times 10 to the 6 metres per second, and it travels through a magnetic field and perpendicular to it of 0.6 Tesla. What is the force on the electrons? Here we're going to need the formula that force is equal to BQV, where B is the magnetic field, Q is the charge, and V is the velocity. So now it's just a case of filling in. B is 0.6, Q is the charge on an electron, which is 1.6 times 10 to the minus 19 coulombs, and the speed V, or velocity, is 4 times 10 to the 6 meters per second. And if you multiply all of that out, you should get that that equals 3.84 times 10 to the minus 13 newtons. And now we come to the tricky bit again. In which direction does that force apply? Once again, we've got to use Fleming's left-hand rule, but remember, if the electrons are flowing from left to right, conventional current will be flowing from right to left. So the current now has to flow in the direction of my second finger. The field, which is now pointing in the right direction, north to south, is pointing upwards, which means my thumb is pointing into the page, and so the electrons will be deflected into the page. And because the force is always perpendicular to the velocity of the electrons, this means that in fact the electrons will be bent round into a circle into the page. Question 3. We've got a beam of electrons going from left to right at 3 times 10 to the 7 meters per second, passing through a magnetic field of 0.4 millitesla. And the question now is, what is the radius of the path? Well, I don't need to do any contortions because I've got exactly the same setup as the previous question, so I know that the electrons are going to bend into the paper. The question now is, what is their path? Well, the force that is acting on them is equal to BQV, just as we had before, and that force is going to provide the centripetal force that keeps them in circular orbit. And the centripetal force is equal to mv squared over r. If you simply rearrange this formula here, you'll get that r is equal to mv over bq. And now it's just a case of substituting in. You get r is equal to the mass of an electron, which almost certainly you'll be given. It's 9.11 times 10 to the minus 31 kilograms, times the velocity, which we were given as 3 times 10 to the 7 meters per second, divided by the magnetic field, which is 0.4 times 10 to the minus 3 Tesla, times the charge on the electron, which is 1.6 times 10 to the minus 19 coulombs. So now it's just a case of putting that into the calculator, and you should get that that is 0.427 meters. So the radius of the circular orbit that the electrons will take as they bend into the page is 0.427 meters. Question 4. We have what's called a velocity selector. A velocity selector consists of two parallel plates on which there is a voltage or electric field. This is the positive, this is negative. And we have a perpendicular magnetic field, which, as you see, is coming out of the paper. So north is into the paper, south is out of the paper, and we fire a beam of electrons this way, and the electrons pass through these two fields undeflected. Now, of course, what the electric field will do is to cause the electrons to move towards the positively charged plates, but the magnetic field, if you do the Fleming's left-hand rule, will cause the current to flow towards, or to flow downwards. And if the electrons neither turn up nor down, it means that the two fields, or rather the forces caused by the two fields, are exactly balanced. And the question is, what is the velocity of the electrons if the electric field is 3 times 10 to the 4 volts per meter and the value of the magnetic field is 1 millitesla? Well, we just need to know what the forces are in relation to the electric and magnetic fields. For an electric field, the force is equal to E times the charge on the particle. For a magnetic field, the force is equal to BQV, and it is V we are trying to find. If there is no deflection, those two forces must be equal, which means that EQ is the force here, must equal the force here, BQV. You'll see that the Q's cancel, and that simply gives you that V is equal to E divided by B. The value of the E field divided by the value of the B field. Well, E was 3 times 10 to the 4. B was 1 times 10 to the minus 3 because it was 1 millitesla, and that gives you a velocity equal to 3 times 10 to the 7 meters per second. So that's a way of determining the velocity of electrons in a velocity selector. Question 5. We have a coil, and through that coil and perpendicular to it is a magnetic field. The magnetic field is 3 times 10 to the minus 3 Tesla. The cross-sectional area of the coil is 0.3 meters squared. The first part of the question is, what is the flux through the coil? Well, flux we know is equal to BA, so that's simply going to equal B, which is 3 times 10 to the minus 3, times the area, which is 0.3 meters squared, and that comes to 0.9 times 10 to the minus 3 Weber. Part 2. If the coil has 100 turns, what is the flux linkage? Well, now we know that flux linkage is going to be BAN. Well, we just calculated BA, that's 0.9 times 10 to the minus 3, and N is the number of turns, which is 100. So that's going to come to 90 times 10 to the minus 3 Weber. Now we're told that over a period of 3 seconds, the magnetic field reduces from 3 times 10 to the minus 3 Teslas to 1 times 10 to the minus 3 Tesla in 3 seconds. And the question is, what is the EMF that is generated? And we're going to use the formula that the EMF is going to be minus the rate of change of flux, or flux linkage, which is going to be minus dBAN, that's minus ddt of BAN. The only thing that's changing is B. A and N are going to be fixed, so what you're going to get is essentially minus then the change of B is from 3 times 10 to the minus 3 to 1 times 10 to the minus 3. Well, that's a change of 2 times 10 to the minus 3 divided by the time, which is 3 seconds. So that's essentially d by dt of B. It's the rate of change of B, times the area, which of course is 0.3 meters squared, times n, which is 100, and that will come out at minus 20 times 10 to the minus 3 volts. Sorry, minus 20 times 10 to the minus 3 volts. The minus, of course, purely indicating that it opposes the change that caused it. Question 6. A rod of 20 centimetres in length is moved at a velocity of 10 metres per second through a magnetic field of 5 times 10 to the minus 6 Tesla, and you'll notice that the magnetic field is going into the paper. And the question is, what is the EMF that is generated? Well, in order to get the EMF, we say that EMF is going to be minus the phi by dt. That's minus phi is BA, so it's minus dt. What is the area? The area is the length, which is 20 centimetres, times the distance covered. So that's going to be minus d by dt of B, which is unchanging, times the area, which is L, that length here, 20 centimetres, times x, the distance travelled this way, that's going to be an area. But if you look, dx by dt is velocity. So this simply reduces to minus b times L times dx by dt, because x is the only thing that's changing, and that's velocity. So now we need only put in the values. B is 5 times 10 to the minus 6. The length was 20 centimetres, which is 0.2 of a metre, and the velocity was 10 metres per second. And if you put that into your calculator, you should find that the EMF so generated is 10 times 10 to the minus 6 volts. Question 7. I have a transformer with 200 turns on the primary. I have an input voltage on the primary of 12 volts, and I want an output voltage, that's the voltage of the secondary, of 3.5 volts. How many turns do I need on the secondary? Well, we need to remember that NP divided by NS is equal to VP divided by VS. So that means that what we don't know is the number of turns on the secondary, and that means that NS, if you just manipulate this formula, NS is going to be equal to NP divided by VP times VS. Well, NP is 200, VP is 12, and VS is 3.5. And put that into a calculator, you should, I think, get 58.3 turns. You can't have 0.3 of a turn, so you'll need 59 turns in order to deliver 3.5 volts. Part 2 of the question, if the current through the primary is 2 amps, what is the current through the secondary? Well, here we need the formula that N primary divided by N secondary is, and now for current it's the other way up, so it's I secondary divided by I primary. What we don't know is the current in the secondary. The current in the secondary will be N primary divided by N secondary times I in the primary. So IS is going to equal, well, the number of turns in the primary is 200, we were given that. The number of turns in the secondary was 58.3. We calculated that, and we're told that the current in the primary is 2. So we multiply by 2, and that should give us a current in the secondary of 6.86 amps. And the third part of the question is that if the power that you get out of this transformer is 12 watts, what is the efficiency of the transformer? Well, of course, the efficiency will be the power out divided by the power in. The power out, PO, let's say, is 12 watts. That's what you've just been given. The power in is going to be the voltage times the current. Well, the input voltage was 12 volts and the input current was 2 amps, and that's going to be 24 watts. And so the ratio of the output power to the input power is 12 over 24, which is 0.5. And therefore this transformer is actually a very bad transformer. It's only 50% efficient. Where is the other 50% of the power gone? Well, probably in heat. The transformer is going to get very hot. Question 8. We have a coil in a magnetic field, and the point about this coil is it can be twisted so that it rotates on an axis like this, and there are 400 turns on this coil. The cross-sectional area of the coil is 0.02 meters squared, and the magnetic field in which it is turning is 1 Tesla. First part of the question, what is the flux linkage when that coil is at an angle 30 degrees to the field? Well, flux linkage is equal to BAN times the sine of the angle, and that's going to be B, which is simply 1, times the area, which is 0.02 meters squared, times the number of turns, which is 400, times the sine of 30 degrees, which is a half. And if you multiply that out, you should get that that equals 4 Weber. Secondly, or second part of that question is, if that coil is rotated 50 times a second, 50 hertz, which is the frequency of electricity in the UK, what is the peak voltage that you will get out of it? Well, we recall that phi is going to be BAN, and now when you are actually changing the angle, that is going to be times the sine of omega t, where omega, of course, is the angular velocity and t is the time at any point. And the voltage, or EMF, is going to be minus phi by dt, which means that you're going to get a voltage of minus BAN. You bring the omega outside and change the sine to a cosine. So that is the voltage, and the peak voltage will occur when the cosine of omega t equals 1, because the cosine of omega t never gets greater than 1, so the peak must be when that equals 1. Consequently, the voltage will equal minus, well, of course, the peak voltage will be between plus and minus, so in that sense, you can actually write plus minus because it will be an alternating current and therefore an alternating voltage. So it will be B, which is 1, times the area, which was 0.02, times the number of turns, which were 400, times omega, which is 2 pi times the frequency. So that's 2 pi times the frequency, which we were told was 50 hertz. And that's going to come to 2,500 volts. And so you're going to have a voltage, an alternating voltage, which is going to look like a sine wave, where the peaks are going to be plus 2,500 volts and minus 2,500 volts. That's a lot. But bear in mind that I had given us a magnetic field of 1 Tesla, and that's a huge magnetic field. Normally you wouldn't get a magnet with anything like that kind of power.